So, welcome everyone. Glad you could make it after the booze cruise from last night. So, of course, our software has no bugs. The hardware we run on has no issues, and everything works as it should. So we're all happy campers. However, sometimes we do need to debug something to inspect our system and analyze what's going on. And we've always had tools such as Dtrace, GDB, or even good old DDB to help us analyze and debug our problems in those rare cases where we have them. But sometimes we need a tool that allows us to dig deeper into the system and to give us a more holistic view of what's going on. And Dtrace can be a valuable addition to the list of tools we already have. So Dtrace is the dynamic tracing and analysis tool originating at Sun, or at least made production ready by Sun. And it's found its way into many other systems. So it was initially developed for Solaris, and of course FreeBSD, NetBSD, macOS, and Linux all have an implementation these days. So today I'd like to talk to you about the efforts in OpenBSD, and the ongoing efforts, I should say, of perhaps eventually someday, maybe we'll have Dtrace proper. So first we'll have a quick look at Dtrace. What it is and why we should care about it. Then I'll go into CTF, give an overview of the current state of affairs of CTF and Dtrace in OpenBSD. So for those of you who don't know me, Jasper Adriaanse, or Jasper for short. Been involved with OpenBSD since about 2006. Mostly, working in ports, and in particular GNOME. Been playing with Octeon, and more recently true random number generators for the URNG driver, and of course CTF. So by day I work as a Unix engineer at Snow in the Netherlands, and by night I hide behind these aliases on GitHub and Twitter, so you can stalk me or harass me if you prefer so. So perhaps a long time from now, in the source tree, still far away, but at least the DDB and CTF part have been undergoing for a little over a year now, and was mentioned the purpose of this talk is to give you a status update of where we are and the efforts that went into it. Of course, brief explanation of Dtrace and CTF itself. So let's start with the end game or end goal first. It's our goal to have Dtrace one way or another, but it does require many other pieces to be in place first. An analogy I've been using in the past couple of days to describe to people where we are and how far away we are from having Dtrace is picture a puzzle. So we have the corner pieces, we found them. We're working on filling in the edges, and we sort of know what the picture or the puzzle should look like when it's completed by looking at other systems. And we're slowly but surely working on filling in the missing pieces, which at this point are still a lot. So what is Dtrace really? It's, as the name implies, a dynamic tracing framework. The way it works is that it's using minimal impact probes, which don't have any effect when Dtrace is not enabled, and have a minimal or as small as possible effect when it is in place. So as I mentioned, it was made production ready by Sun in 2003, publicly released in Solaris a couple of years later, and since it's found its way into macOS around 2007, FreeBSD, NetBSD, and Linux followed shortly. There has been an attempt to port Dtrace to QNX. However, just like QNX's future, it's sort of unknown. And Dtrace is CDDL licensed, which may not be an issue for certain systems. However, it's a clear blocker for OpenBSD. So that's the main reason why we cannot simply take the original source code of Dtrace and of the tools around it, such as the Ctf tools. So we cannot import those because of licensing issues. So Dtrace works with providers and probes, which I'll show a bit more about in the next slide. But also want to mention D, the language D, which allows for writing scripts. Of course, the main way of interacting with Dtrace is by writing D expressions on the command line. And Brandon Gregg wrote the Dtrace toolkit, which is a very comprehensive set of scripts, all using Dtrace, but providing top or IO Snoop-like functionality. So this is one way to, a very short demonstration of what Dtrace looks like. So you call Dtrace and you provide it with a probe to use. In this case, we're using a wildcard. So we're using the syscall 3:entry probe, which means that there's a wildcard in there. So with the syscall provider, then two namespace separators and an invisible wildcard, a colon, and the entry. So what that means is what we're doing right here is for every syscall that gets entered, hence the entry probe, we print or we trace the executable name. So for example, as you can see, when we fire up Dtrace, you see that's entering the IO control syscall twice, and then QEMU comes along and does some other things. And this sample was taken from SmartOS. So as you can see, we're not inspecting a single application here. We're instrumenting the system as a whole. I didn't provide any application to trace, and you can see that Dtrace and QEMU are running. So another slightly more complex example, but still near trivial, is to show the number of bytes written per process and summing them. And when you quit Dtrace, it'll print its summary. And based on this, you can analyze your system further, create some fancy graphs. And these were taken from Brandon's Dtrace one-liners.txt, which, if you don't know it, it's a small treasure trove of neat one-liners, such as this one. So why should you care about Dtrace? If you know Dtrace and if you've used it, you probably consider it a valuable and very handy tool. But if you don't, why should you be interested and perhaps to get involved in the effort in OpenBSD? So we have a number of tools: Truss, Ktrace, Strace, and Ltrace, of which the latter two we have on OpenBSD already. But they're syscall tracers or only for tracing userland. And while these tools certainly have their application, they may give you a too narrow view of the system. And Dtrace also addresses the observability problem. So what that means is when you inspect something or observe something, the thing you're observing is affected by you looking at it. For example, if you're K-tracing an application, it may behave differently from when it's running un-K-traced, which is quite the opposite of what you're doing, since you're observing bad behavior, for example, and you want to see why that's happening, and you're K-tracing it, and it may end up doing something else or behaving slightly different ways than what it's doing otherwise. And Dtrace does not exhibit this behavior. And also, Dtrace allows for very, very fine-grained inspection, albeit short-term. You wouldn't want to write your monitoring scripts or long-term analysis using Dtrace. There are more appropriate tools for that, since it's more for short-term inspection and debugging and analysis. And speaking of inspection, you've probably all seen the shouting in the data center video. If not, I urge you to look it up on YouTube. It's a prime example of how to use or abuse Dtrace to observe what's going on in your system. And of course, with a more complete tool chest of tools, you don't need printf debugging anymore, or, well, let's not overstate the case, less at least. So how does Dtrace actually work? So there are a number of providers. For example, the Cisco provider that I showed earlier. There's the IO provider, the sysinfo, but also FBT. That's the function boundary tracing provider. Of these, FBT will be the first targeted provider in OpenBSD. So providers provide probes. We saw the Cisco entry probe earlier using the wildcard, and here where, for example, the Cisco execve entry probe is just for inspecting the execve syscall. So the FBT probe works by patching the function boundaries. So as soon as you are about to execute a function, the function prologue will be dynamically altered or patched. It saves the original instruction you were about to execute. It then runs the probe, which does whatever it needs to do. And when the probe is done running, it'll emulate the original instruction you were about to execute when you entered the function. So currently we do have code for this in OpenBSD already. It was committed by Martin during or shortly before the general hackathon in Cambridge. Although right now it's hidden under the DDB prof kernel compile time option. But it's the first real code we have for tracing or probing. So when a function is about to return, the last step would be to execute the probe if it needs to do that. And when the probe is done processing, it'll emulate the last instruction of the function, and the function itself returns normally. So from an outside point of view, nothing happened. The function still did what it needed to do. It just got its prologue and epilogue altered. So one key thing with Dtrace compared to other tools is that it saves its results in per CPU buffers, and it doesn't directly export these back into userland. So you're not running into the top problem. So if you're running top on a system with a lot of processes running, you'll see that top itself will be one of the processes consuming most CPU time. That's because it's continuously gathering the information and directly providing it back to you. Whereas with Dtrace, it'll, by default, on 1 second intervals, it'll collect the data, and at the given interval, it'll export it back to userland. So you're not continuously impacting the application or system you're tracing, with the tool that is tracing it, and they're playing or they're battling for CPU time. So that's a key feature of Dtrace. Of course, Dtrace needs to know about what functions are, which symbols are available, and their types. And that's where CTF comes into play. No, not this CTF. This one, the compact type format. So CTF can be considered a compacted notation of labels, functions, and for the other types that it supports. This is the full list. It's generally, though in practice, basically always compressed with zlib. And there are two versions of CTF available, but within OpenBSD we only target right now the version 2, the latest version. Version 1 isn't really in active use anymore, so there's no reason why we should develop our tools to use that. On Solaris, CTF is extracted from steps, whereas on other systems it's using Dwarf. So Dwarf is generated by the compiler. When you compile your source code with the -G option to generate the debug symbols, the compiler will keep track of everything that might be useful for future debugging and saves it into several sections in the ELF object file. However, because Dwarf is so huge, it's not feasible to distribute kernels that always have this extra information added. So for example, kernel built with all the debug options, all the debug information stored in it is about 4 times bigger with all the Dwarf parts compared to just having CTF. Back in August, when we enabled including CTF in all the kernels, the growth was about 1 to 2 meg. That's including the natural growth that just happens during a hackathon. So the CTF data gets stored into the ELF object file as well. It can be distributed as a separate binary data file. However, in practice, it's always stored in the standard.sunwctf section. So when you look at a kernel of OpenBSD these days, you'll see that it does have this particular section, which means that it does have all the CTF data of all the symbols, functions, variables, strings, you name it, it's in there. So it can be considered a subset of Dwarf, but in reality it's more the extracted form of whatever is relevant for Dtrace or CTF or, in our case right now, DDB. Dwarf also supports many other languages than what we care about in our kernel. We don't care about Pascal or Modula or C++ or whatever. CTF is only concerned with C, pure, simple C, no assembler at that either. So Dwarf also contains information on line numbers to be able to map your code into line numbers and file information. That is not part of CTF. However, it is information we are quite interested in providing. So right now for a developer to extract that information, they have to be running a kernel which contains all the debug information. However, we generally, we don't recommend users running this kernel. So when they do run into a crash, we have to provide them with this kernel so they can re-trigger the crash, get the relevant information, and it would be so much simpler if we could also save this information in some way. Not part of CTF, but it's something that Dwarf provides. So here's an example of CTF dump. It's one of our own CTF tools. So running this on the BSD kernel just shows the header with the CTF magic number, the version encoded, and further information that's relevant to parsing tools of this fairly simple and structured format. It's not like Dwarf, where you have your compilation unit, your debugging information entry, and all sorts of extra tags and fields that you need to parse in order to get whatever is relevant. So for Dwarf, the relevant information is stored primarily in two sections: the info, debug info, and debug abbreviation section, abbreviated to abref. So within the compilation unit, a die is generated for every variable, type, function, etc. And these dies themselves can be tagged with whatever is applicable to this die. So it can be tagged as a variable or a pointer, as well as attributes relevant to it. And because dies can be nested, it creates a tree-like structure that tools like Dwarf dump are able to traverse and dump a representation of the the Dwarf information. So this is some output of Dwarf dump with all the information it knows about this object file, and most of it is quite relevant to a debugger, but not for CTF. Quickly going back. So the Dwarf code that gets generated on OpenBSD right now is Dwarf 2. And newer versions of Dwarf have been released in over recent years. So for example, version 3 added support for C++, or better support for C++. Fortran 90 allocatable data version 4 came with better compression, which is interesting, but also support for C++ 10, which, well, we have no use for in our kernel. Luckily. Version 5 was released earlier this year, standardized actually. And came with many other improvements, such as way better compression still, faster lookups, better annotations, and descriptions. However, the compiler we have right now doesn't fully emit Dwarf 5, but it may be at one point interesting to move further along with what our tools can use, since they're currently still limited to version 2. So, Ctf Tools. It's great to have an object file which contains the Dwarf information, but in order to make something useful out of it, to turn it into CTF, we need a number of tools. So Solaris developed the Ctf Tools package, which contains Ctf convert, merge, and dump. However, they're CDDL licensed. So there was a blocker for us to move forward with CTF, since we couldn't import it into our tree. Back in 2016, we did import it into ports, where we're a bit more lenient when it comes to licensing, and it's using the libdwarf and libelf libraries, which we don't have in base either. And it was quite the effort to find the right combination of libelf or not using libelf to port the Solaris specific data structures to OpenBSD, which applies specifically to Ctf Merge. At some point, we may also want to use libctf if we have enough consumers in the base system. Right now, we only have a very small number, but as its usage increases, we could also distribute that as part of the base system. It is part of other operating systems, on the other hand. So having the CDDL licensed Ctf Tools and ports was a great Kickstarter for us to move forward. Not worry about this part of the problem, but actually move forward on using the CTF data. So MPI set out to creating a new implementation under a more liberal license that it is fit for inclusion in the OpenBSD base system. So we ended up with CtfConf, which has functionality similar or equivalent to Ctf Convert. We dropped Ctf Merge. I'll tell you why in a bit. We have Ctf Dump, which is a visual representation of the CTF data, which is a very helpful tool in verifying that CtfConf actually works and generates what we expect it to. And then we have Ctf Strip. And this is a really nice trick. So our kernels now get built with -G by default, so they generate all the dwarf data. And then we strip them. But we're not using the regular strip. We're using Ctf Strip, which does Ctf Convert on the object file. And if that fails, it'll fall back to plain strip, which removes all the dwarf data, and we end up with a regular kernel, no CTF. However, if Ctf Convert worked, it wrote out the CTF data into a separate file, which we then use opscopy to insert back into the object file. And that's basically what Ctf Merge does. It takes all the object files and merges all of their CTF data into a single representation, which then gets inserted into the final object file. That's quite a complex process, the merging itself, but also to insert the data into the object file. And we have opscopy in base, so why not make a small little shortcut and use what's there already. Maybe at some point we can add more smarts to Ctf Strip, but then we basically end up implementing large parts of opscopy in Ctf Strip. So yeah, why go there? So that said, we do have CTF data available for all our platforms right now. We have some support for it in DDB, which allows all the platforms to make use of this. There are some portability or tasks related to portability in other parts of this effort, but CTF is available for all our platforms and all our kernels. So this is a quick example of running Ctf dump on a kernel from a couple of weeks ago, displaying the strings available in the object file, or the kernel in this case. So the first column are the indices, which are referred to from other parts of the CTF data, as we can see right here, for example, for the types. So in this representation, we can see that the type integer has index 12. Its encoding is signed and the others, it's a long list, so I just snipped it for brevity. But here we can see how it's used. So for example, the db_num_args function, which is used by the trace command from DDB to look up the number of arguments that a function has. So its index is 4009, and it returns 12. The 12 refers back to the, where's my cursor? Yeah, so the 12 up here refers back to the 12 up there. So we know that db_num_args returns an integer, which in this case is the number of arguments. We can also see that its arguments are of these types, which is a pointer, which refers to a struct. So we know that the first argument of db_num_args is a struct, call frame struct. And we can defer the rest based on what else is there. So this is also an interesting way of parsing all your functions and mapping their types and their arguments. So DDB. DDB is the in-kernel debugger of all BSDs. And it was actually the first consumer of CTF data. So back at the hackathon in 2016, we started working on CTF, and we needed a way to verify that the work we were doing was valid and would actually lead to somewhere. And DDB seemed like the obvious starting point, which for me was a very fun and challenging project during the hackathon to dive into the bootloader in order to load the CTF data, as well as an adventure into DDB. So from within DDB, we can inspect the CTF data of the currently running kernel. So when the kernel gets loaded by the bootloader, the .snw CTF data gets loaded, and DDB knows where it's loaded at, and when required, it's using that data, for example, for trace. So trace on AMD64 and i386 at the time, it showed you the function names, but it couldn't figure out how many arguments the functions had. Other platforms such as SPARC64 did have architectural advantages, and they could figure it out, but AMD64 i386 couldn't. Later, the pprint commando or command became CTF aware, and most recently, the show struct command as well. So this is what trace looked like in DDB before having CTF. So as you can see, it has no idea of the number of arguments, and with DDB, so DB enter still doesn't have any, but the others are properly filled in. So that was the first validation of, wow, so it's actually working what we're producing, even though it's with the original CTF tools, but still the way we're integrating it into our kernel does work. So pretty printing and CPUs, or pretty printing in general, is using the CTF data in order to figure out how to represent the kernel data as something human readable and defer the types from it. So as you can see, we're printing the DB CTF variable. And right here we have the CTF header. So using the show struct command, as we know that it's a struct, we can also print that and see everything that's contained in it. So this is the CTF header data of the kernel that's actually running right now, or at the time. So where are we at right now? The dynamic profiling part from MPI was committed during the 2016 General Hackathon, and at that time we really made some great efforts into getting started and figuring out all the components needed, at least CTF-wise. So we imported the original tools into ports. They're still there at the moment, even though we have our own free tools in the base system, but they still serve as a useful reference implementation. And at that hackathon, the original DDB code for CTF was committed as well. And then about a year later, the tools were imported into base, and we actually built CTF-enabled kernels by default. So this was a huge step in moving forward and getting CTF to the people, as it were. So sometime after the hackathon, actually, one of our developers, DOG, committed code to remove the old DDB struct kernel compile time option and have show struct use CTF. So there was another way of moving forward and validating the effort. And as you can see, the hackathons have been tremendously important in the development of, well, not only CTF, but of OpenBSD in general. So, well, they're sponsored by the OpenBSD Foundation, but essentially funded by you, so keep them coming. Of course, there's still a lot more work to be done. For example, we could make an effort in catching up on modern or more recent dwarf versions. We could cut out CtfConf and see if the compiler could actually be made to work for us, since it already knows all the types and everything that has to go into dwarf. Why not make an intermediate step and generate CTF right away? Of course, there are some portability issues to be addressed still. So for example, the dynamic profiling part is only for MD64i36 at the moment. And we can extend the usage of CTF for trace into other architectures as well, because most of them have been relying on their internal resolving of the number of arguments. But why not make use of CTF since it's there? And of course, eventually, we may have Dtrace. It's still long ways down the road, but we're making an effort and getting the word out to people and getting people interested and involved. That'll really help to get this completed. So to recap, we have our own ISC licensed Ctf toolchain in base. All our kernels are built with CTF data and properly inspectable through DDB. Still a long way to go, but we're making good progress. Of course, you can help. So I'd like to thank MPI for all his hard work at getting us started, writing the tools and being mental support. Of course, the EuroBSD Foundation for inviting me here, and Snow for having given me the time to attend this year's conference.
Any questions? How much time does the Ctf script take on other architectures? I'm not convinced that all these days are 64 about 40 minutes to use.
Well, it's not 40 minutes. It's part of the build process. So it's something that users don't see or don't notice a delay when they boot a kernel. On a fast AMD 64 machine like this laptop, it takes, I don't know, I've actually not verified or tested how long Ctf script takes on, ARM32 or something less fast, but it's probably several minutes and not 40.
No, but I mean, not specific program between Malaysia and CTF Tools, but I find it very good to actually have CTF Tools and then CTF Merge, because then you don't have the usual practice of streaming
Yeah. Yeah, definitely, and I think we should spend the time as well to look at other architectures and see the impact there and extend and improve on those as well. Yep.
Any other questions? So in the Solaris implementation, is this idea of personal from Dtrace? I know this is very far off, but you've got some thoughts about doing some thoughts as well.
Yeah, so with the load bits ELF flag, I believe that data gets also, the CTF data also gets written out to your core file, and then you can do post-mortem analysis on your userland binary at least. For now, our effort is mainly focused towards the kernel, but yeah, it will be well, quite helpful to do post-mortem analysis and debugging eventually.
Any more questions?
Thank you.